This is the third lecture or third video related to energy economics as applied to climate change. In other words, we're going to look at the penetration of renewable energy into existing electricity grids. And what we're going to look at is the merit order or supply stack. Now that works as follows. Various generators bid in the amount that they would like to produce in 24 hours from now and the price that they would like to receive on a per megawatt hour basis. Now, they would, of course, try to bid in at their marginal cost, except they will bid in at zero if they want to ensure that they will operate. If they want to export electricity to another jurisdiction, they would then bid in an extremely high price, which would guarantee that they would not be taken, and as a result, they would be free to export their electricity. So let's look at the supply stack, which is given by this line here, this jagged supply, and each horizontal segment represents a different marginal cost and a different generator or group of generators. So the baseload power plant, a coal plant, a nuclear power plant, or some other baseload plant wants to ensure that it's taken, so it bids in at zero. It knows that it's going to get whatever price is going to clear the market, except for the situation if the demand happens to be, or the load happens to be exactly the base load. If demand or load in that particular hour is at D0, then the price will be determined by G2, generating facility G2, assuming that G2 would be able to produce only part of the capacity that it asked to be used in 24 hours time. Now, if Dn happens to be the load, then there is no supply and we have blackouts. Now, the stack supply and rents, when you have some demand response that causes that demand function, instead of being vertical, it has some slope to it. In this case, the baseload demand would look like this, and it would intersect here, so the price would be zero. There are instances when the price in a particular electricity grid does go to zero, and it can even go to negative if, for example, the grid needs to get rid of electricity and it sells the electricity abroad at zero price, or is paid or pays for another grid operator to take it from it. Now, if the price happens to be P0 and the marginal generator is able to operate at anything but full capacity, then the price will be P0. If it cannot operate at anything but full capacity, then the price would be determined by G3, which would mean that G2 would fall out, this would all shift over, and the intersection would occur up here, and the price would be much higher. But assuming the price is P0, the baseload generators will then earn a quasi-rent or producer surplus, if you like, of QR0, and generator G1 would earn a quasi-rent producer surplus given by QR1. Now, suppose that we look at this a bit further. Notice that in this case, the intersection of D0 occurs at the vertical section here. So what would be the appropriate price? Well, if the price were set by G3, then there would be less demand. If it were set by G2 at point C, as it was in the previously, then what would happen is there would be an excess demand at point B. So therefore the price has to be set at A, and the operator G2 would also be earning quasi-rent, as would these other ones as well, although we might call it a scarcity rent, although it probably would be inappropriate to term it that at this point. So this area here, each of these generators would earn an extra producer surplus because the price P0 is determined by this particular intersection. Now suppose we were at the end of the supply stack over here. We had no further ability to supply more electricity. In this case, the marginal generator would be G3 and the price would be determined by P1, in which case this area here would indeed be considered scarcity rent, because there's a scarcity of electricity available in the entire system. In that case, we have to be careful that we are able to charge P1, because there are instances where the price of electricity is capped by the system operator, often due to political reasons. For example, the cap on the Alberta system is $1,000 per megawatt hour. In Texas, it used to be about the same, but then with problems, they upped it to $5,000 per megawatt hour. But even at that, sometimes you end up with blackouts because the price is simply too low and the market does not clear. So one has to be very careful. And recall that the scarcity rent, in the case of some generators, particularly the marginal ones, would be required in order to meet, to encourage investment in those kind of facilities. Now, here would be the market order if we include a number of different generators. So for example, here we have base load generators, and if D star occurs, they'd be the only ones operating. Here we have a combined cycle gas turbine, another coal plant, a smaller one perhaps, a biomass plant, combined cycle gas turbine 2. We have an open cycle peak plant here, another peak plant. And if demand is given by this line here, then the price would be P. If, however, we have the problem that this plant cannot operate at anything but full capacity, then then OCGT 3 would come into play, in which case the price would go to P prime. Now, here we have a market merit order or a supply stack with wind included. All right, notice that there's been a shift in that supply stack so that it shifted from Q star to Q0. If we have a situation where the demand is D star, in other words, the base load demand, then we would have to either reduce the production of base load generators, or we'd have to prevent wind from coming into the system. All right, again, the price is solved in the same way. In this case, we would have PF would be the price that clears the market. If OCGT came into play, then OCGT2 rather came into play, because OCGT1 could not handle operating at anything but full capacity. Then with that price, you would end up here at P, and demand would be less. So by going to the open cycle gas turbine 1, you would actually increase the amount of electricity that's being used. Notice up here that we have hydro for export is extremely high on the merit order, and a diesel generator is also high because it is expensive to operate. Now we can get some more detail on the market merit order with and without wind by looking at this diagram here. So this is the supply stack, the solid line without wind, S0, but with wind it looks like this. The problem is that with wind being intermittent, this dotted line, this dashed line rather, this dashed supply curve may be shifting back and forth over time. All right, so we have then a problem that that we have to take that into account. All right, so if the wind is in, then the price would drop with the wind, and there would be a slight increase in the amount of electricity that's being demanded, given that the demand D0 is downward sloping and it has some slope to it instead of being completely inelastic. If, again, the wind were to die down, then the price would actually go up as to P0. So the wind does reduce the price, and it means that all of these generators here, this area here, would earn a lower amount of producer surplus. So there's a reduction in producer surplus or quasi-rent. Now, what happens if the demand were to become even more elastic, so DM as opposed to D0, it would make very little difference in what happens if there was no wind, but with wind, it would reduce the price less, but there would be more electricity generated. So you see that jump here. So we also need a reserve market. So with wind, it has an effect on the reserve market. So reserves consist of regulating reserves, which deal with short term, meaning seconds up to 10 minutes, fluctuations in load. So we need regulating reserves that can move within this seconds to 10-minute framework, can fluctuate within that framework to be able to deal with fluctuations in load and meet those. So base load plants have a little bit of wiggle room. Gas and diesel generators operating at part capacity. So an open cycle gas turbine or diesel fuel generator could be in that situation. They're running, but not not at a high level. They're just idling. We can have standby reserves, which are called spinning reserves, which is really an idling. Load following reserves that deal with anticipated changes in load over an hour are also a form of reserve. And then we have contingent reserves. The Western Electric Coordinating Council rules require sufficient reserves to meet failure of the largest unit online plus some percentage of thermal generation. So generators bid into this reserve market. So they get a capacity payment. So this is the capacity payment. It could be, so a hydro facility would bid in for capacity payment 1. An open cycle gas turbine might be willing to come in, all right, but needs to be paid in order to produce the plant, to build the plant. And we may have some other gas plant as well. So the price then is determined by the demand for capacity. Here the capacity would be paid is equal to CP3. So all of these generators would get this capacity, and some of them would be earning a quasi-rent. Now they would also earn money if they came online, and they'd be paid whatever the price is for that is currently in the on the grid. So the market for regulating and contingent reserves looks like this. It's got a supply stack as well. Now you could have an import that is important, and generators would receive payment for the reserve position, so the capacity payment, plus the market clearing price if they're called upon to deliver electricity. With wind, the demand for capacity, for reserve capacity, increases from DC to DC prime, which requires additional reserves due to wind, even if overall system capacity is unchanged. That's the important part. Now, why would import A? Well, this is relying on a transmission intertie. So we have to take into account that there could be a need for transmission intertie, and we see countries like the UK depending on and probably paying side payments to countries like Norway for an ability to get electricity from that country if needed. So when we manage wind resources, we find that it's difficult to integrate wind into electricity grids. Wind is variable and intermittent. There's too little or too much wind, so output drops suddenly to zero. We look at the capacity factor, which we mentioned in the previous video, which is the actual generation in 1 year divided by the rated capacity times 8,760 hours. Capacity factors for wind rarely exceed 20 to 25%, whereas capacity factors for nuclear power are around 95%, 90% perhaps, and for coal and combined cycle gas turbines, they're around 85 to 90%. We could talk about wind penetration and measure it as the wind capacity divided by non-wind capacity, which is not the greatest measure. A better measure would be wind penetration, would be wind generation capacity divided by peak load. Now, if we look at wind in more detail, I've got some data here from the Alberta load and wind generation at 10-minute intervals, looking at the first and the last 10 days in 2014. So these are the first 10 days in 2014, and wind was below 100 megawatts January 1, 3, 5, and 7, and capacity factors were 33.5% and 38.1%. So these are pretty good capacity factors. Now, the dashed line represents the load minus the wind. So we take this load, the solid line, and we subtract from it the available wind generated power. Notice one important thing from both of these diagrams, and that is that the dotted line, the dashed line, is much more variable, much more up and down than the other line, which implies that wind is going to cause problems in terms of operating the particular system, the particular grid. And that's the problem with wind. Wind, it may be cheap, but it becomes expensive because it affects the other elements of the grid. Now, for clarity, just to give you an idea of what systems look like, there's quite a bit of difference between them. If we look at Alberta, the generation of electricity by source, 54% comes from natural gas, 36% from coal. Wind accounts for 6%, hydro for 3%, and biomass, thermal, and solar count for very small amounts, 2%, and petroleum for 0.1%. Now contrast this with British Columbia, where 87% of the generation of electricity comes from hydropower. Biomass, remember British Columbia has many forests and a huge forestry sector. 5% comes from biomass and geothermal. 4% comes from natural gas, 2.6% from wind, and 0.5% from petroleum, and a sliver from solar. Now contrast this with Ontario, where 59% is based on uranium, nuclear power, 24% on hydro, 8% wind, 7% natural gas, 1% solar, 1% biomass and geothermal, and a small percent, less than 1% petroleum. So when you're looking at managing these kind of systems, you have to take into account the current generation mix and how that could be affected by wind.